Alright, we're going to be going over Lab 4, which is the Circuits Lab for Physics 2. Whoops. Alright, so the purpose of this lab was to use ammeters and voltmeters to predict and observe the behavior of circuits and currents and potential differences. And we want to apply loop and node rule to better understand them and observe the behavior of different circuit elements, mainly resistors and capacitors. So some important key concepts you need to understand is going to be energy conservation, mainly in relation to voltage and potential difference. The loop rule, basically just overall there is no voltage moving across one loop of a circuit. It will always sum to zero. The node rule of basically a current inflowing into a node of two parallel components. The current in each one of those is in some type of ratio that still adds up to the current that is actually put into that node. Then lastly, you just need to in general know about how capacitors work and how they work within circuits, mainly just in terms of charging and discharging. So, some quick procedures for the initial portion of this was predicting what the current should be using the voltage equation of V equals IR. So we have two batteries, and so we know that the voltage is going to be 3 volts, or 2 by 1.5. We have the resistance, which is going to be in series, so it's going to be added for the 47 and the 100 ohms to get 147, and by going ahead and plugging those into our formula, we get 0.02 amps. Then, if we go ahead and connect a ammeter and it's reversed, what we're actually going to see is that the current is going to register as negative. So in this case, we would get negative 0.02 amps. Then lastly, if we remove one of the amps, we're curious about what the voltage or the potential difference between them are. And in which case, it was found to be 3 volts. And that's because that's the connection between the batteries, basically. And the reason why there's no actual current running is because we've created a break in the circuit, so nothing's closed, so it's actually not running. So then we're going to go ahead and do the potential difference graphs for portions of the circuit, which you can see there. From A to B, we got negative 3 volts. From B to C, there was no change, as it was just a wire. Then moving across from point C to D, we go over the 47 ohm resistor, and we see a drop of voltage of 0.959. And then once again, D to E is a wire, so it's 0. And then across E to F, or the 100 ohm resistor, we see a drop of 2.041 volts, or the remaining voltage. And then the rest is connected to a wire, and an ammeter will act like a wire. So yeah, go ahead and just drawing that up on the graph, you get the following, where basically most of the voltage drop occurs across the 100 ohm resistor, but there's still about roughly a third, if you want to call it that gets dropped by the 47. So yeah. Next, what happens if we throw a ammeter into parallel? So to do this, we went ahead and put an ammeter parallel to the 100 ohm resistor. And then once we actually started measuring the current, you can see that it was 0.06. Now, this is because the current is split between the pathways and follows the node rule. So the current moving into the node has to be equal to the sum of the current within the two paths. And since an ammeter has negligible resistance, it basically acts as a wire. So it's indirectly cutting off the 100 ohm resistor, leading to a new equivalent resistance of 47 ohms for the circuit, which goes ahead and greets the current, so we can still have a 3 volt drop. And then one last thing that we wanted to do was actually calculate how accurate our resistors were, and as well as the resistance of the wires. And to do that, you would rearrange the voltage equation of V equals IR to V over I, in which case V would represent the voltage drop. So for the 47 ohm resistor, it's really good. It's 47.95. But for the 100 ohm resistor, it was 102.05. And then the wire and the ammeters, were treating them like wires, so they're both 0. Next portion is charging and discharging a capacitor. And so when you're charging a capacitor, the brightest it's going to be is at t equals 0. But as time moves on, it's slowly going to start dimming, and eventually the bulb's going to turn off and the current stops because the capacitor is fully charged and now acts like a break in the circuit. Whereas with discharging, the bulb is still going to be brightest at t equals 0, but as time moves on, it's slowly going to dim because the capacitor is discharging, and eventually the capacitor no longer can create a potential difference, so it will basically stop the circuit, and the bulb will turn off again. So moving into the difference in charge time, we saw that for a 10 ohm light bulb and a 20 ohm light bulb, that basically the time was doubled. And that will make a little bit more sense whenever we get to the next part where we're actually looking for the RC value. And so what happened here was I basically took the potential difference across the capacitor and I got time measurements and I got voltage. Then go ahead and using the following equation of V equals V naught times e to the negative t over RC, where RC is the relationship between the charging time. And so from there we have to linearize it, so we go ahead and take the natural log of both sides, and then we go ahead and have the ln of V over V naught is going to be equal to some slope times our changing variable time. So go ahead and doing that, I then go ahead and plot both, and I get a line of best fit, and notice that my slope was negative 0.1447x. So go ahead and taking that, then my RC value came out to be 6.911 seconds, which in the simulation, our RC value was about 6. So overall, fairly accurate. Now, some last questions before I wrap up is, firstly, in a real life situation, an ammeter is going to have some small resistance. So overall, the current reading is going to be less than the ideal situation. You should just be aware of that if you're going to be doing this in person. And if we had a better power source and capacitor, following the model for an ideal situation, it would technically be possible to charge a capacitor upon connection. However, in real life, everything has some resistance, and then there's the element of heat, which changes everything. So it adds time on to actually charge a capacitor. And alright, thank you guys.